start today's session. The first speaker is Dr. Di-Lun Yang. He's going to talk about the review of quantum kinetic theory for spin transport. Please, Di-Lun.
Okay, thank you. So firstly, I would like to thank all the organizers for organizing this very interesting and informative online workshop during these hard times of the pandemic. So I hope one day I will have a chance to visit Trento soon physically. So although this is a review talk, it will be slightly biased because there are also so many talks of the subtopics of quantum kinetic theory in this workshop. So I will mostly focus on my works and try to mention their relations to others' works. Yeah. So let's see. Okay. So I think you have already seen so many introductory slides like this, so I will basically skip the details. So as you know, these recent observations of global polarization of lambda hadrons in heavy ion collisions has triggered intensive studies on the spin polarizations in relativistic matters. And based on these Cooper-Frye formulas for spins, they by the thermal vorticities from the equilibriums lambda hadrons, many theoretical simulations can successfully describe this experimental data. But this is not the end of the story. As you know, later experimentalists further measures these local polarizations, such as this local longitudinal polarization triggered by the local vorticities induced by this transverse expansion. Now this time then we have the disagreements between the theoretical prediction and the experimental data by the opposite sides. So this is the kind of well-known side problems in our community. Also, we also have these disagreements for the transverse local polarization. So I think it's fair to say the local polarization may not be solely contributed by thermal vorticity, and people start to suspect whether there could be non-equilibrium effects which may play a role for this local polarization. So if we look at this typical timelines of heavy ion collisions, in fact, the theoretical studies start from actually the initial state and the final state. But more recently, there are more studies which aim at understanding how these spin polarizations of, let's say, quarks or gluons evolve in the intermediate states, particularly in this quark-gluon plasma phase. Although quark-gluon plasma is strongly coupled, we may still learn some useful physics from the weakly coupled approach based on QCD. One of the renowned examples is possibly this to study this thermalization, or more precisely the hydrodynamizations of heavy ion collisions with the kinetic theories. So the primary goals of my talk will be basically to construct a theoretical framework for tracking the spin transport of pro-fermions, let's say, for example, like strange quarks, when you travel through the weakly coupled mediums, let's say the weakly coupled QGP. Okay. So that's the reason I would like to introduce this quantum kinetic theory. But just like the usual standard relativistic kinetic theory, it has both pros and cons. For the pros, it's a microscopic theory which is related to the quantum field theory, and it can deal with the non-equilibrium conditions. Moreover, it describes the phase-space evolutions of the quasi-particles, which can directly assess the spectrum. But it's only subject to the weakly coupled system, and in most of cases, it's even subject to the weak background fields. However, the standard relativistic kinetic theory only describe, for example, the charge or the energy density transport. So in order to now include the spin degrees of freedom as a kind of quantum degrees of freedom, we have to build up the quantum kinetic theory. So to make my statement about this point is more precise, so basically we can use the quantum kinetic theory to calculate, for example, this is actual charge current density in the phase space, or you can just regard it as kind of spin current phase space density. Then this has some direct relations to this polarization. So I do not want to specify whether this is a polarization for a quark or the polarization for the hadrons. Also, I don't want to talk about whether this is really invariance under these pseudo-gauge transformations. Of course, there also exist some other approaches for the dynamical spin polarization, so please just refer to other talks in this workshop. So here comes to my outlines. So throughout these talks, I will mostly focus on the Wigner function approach for the derivations of quantum kinetic theory, although it can be derived also from other approach. But I think the Wigner function approach has the direct connections to the quantum field theory. So I will start with the QKT for massless spin 1/2 fermions, which is also known as the chirokinetic theory. Then I will move to the massive case, and I will talk about how to include the quantum corrections on collisions. Then I will switch the gears to also discuss about the QKT for massless spin 1 bosons, basically for photons. And then I will make conclusion and outlook. Okay. So let's start with this massless fermions. So as we know, so for the wire fermions, or basically the massless fermions, the helicity equals chirality. So there exists this spin enslavements for the massless particle. So basically, the spin orientations will then be enslaved by the direction of momentums, depending on the chiralities of the particle, of the massless particle. And in fact, this chirokinetic series was initially constructed to study the non-equilibrium anomalous transports, such as the chiromagnetic effect or chiromortical effects related to quantum anomalies. So the point is that for the standard kinetic theory, like this Vlasov equation with the collision term, you integrate over the momentum, then you get the conservation of charge current. But that's not insufficient to describe the quantum anomaly. For example, for the right-hand fermions, we have the chiral anomalies that by these electromagnetic fields on the right-hand side. So we have to include this kind of quantum corrections to introduce, modify Boltzmann or Vlasov equations with the chiral anomaly, and also the spin-orbit interactions, which is necessary to describe this chiral vortical effect. And in fact, this kind of studies also started with some non-field theory constructions, which is more phenomenological. So these gentlemen introduces these quantum objects such as the Berry phase and the side jump phenomena. Again, this is related to the spin enslavements of the massless particle. For side jumps, it's basically this spin enslavements plus the angular momentum conservations. So they introduced this kind of quantum object to modify the classical equations of motions. But later it is found that we can actually construct this quantum kinetic theory or chirokinetic theory from a field theory basis approach, that is the Wigner function approach. And from there, we can construct the covariance chirokinetic theories with both the background fields and collisions. Okay. So I think you also have already heard many talks about the Wigner function. So I will just briefly review it. So I am particularly just interested in these greater or lesser propagators formed by, let's say, the Dirac fermions. So here I also consider the massive fermions. So this is the expectation value of these 2-point functions of the Dirac fermions is defined from this kind of real-time formalism. And you just make the Wigner transform to get their phase space distributions that are the so-called Wigner functions that I'm interested in. And I'm also particularly interested in just the lesser propagators. And the dynamics of these Wigner functions will be governed by the so-called Cardinal band equations, which you can derive from, for example, the Dirac equation plus these Schwinger-Dyson equations. But in order to write down these equations more concisely and to solve these Wigner functions from the Cardinal band equations, we will adopt the so-called H-bar expansions. And that is basically just the gradient expansions. So here I have to assume that the momentum scales of this system is much greater than the gradient scale. So that's the reason why this approach then is also subject to the weak fields limits. And here I also include the collision terms as characterized by these lesser and greater self-energies. So the details of this expression will depend on the systems you consider. Moreover, I will only consider the self-energies as contributing to the scattering process. So I will not talk about the contributions which lead to the modifications of the, for example, the dispersion relations led by the collisions. Okay, so then with this, one can perturbatively solve for the Wigner functions. However, for the Dirac fermions, it's more convenient to decompose these Wigner functions into these phi real coefficients based on the Clifford algebra. And these phi real coefficients, they have different physical meanings, and they are also not really independent of each other. But I will mostly focus on these vector components and the actual vector component, because they basically contribute to this vector and the actual charge current density in the phase space. So for example, you can calculate the vector and the actual charge currents, or even the energy, the symmetrics or anti-symmetric energy momentum tensors from these V mu and A mu's here, okay? So if I input this decomposed Wigner function into the Cardinal band equations, I will get 10 equations. But there exists some redundant degrees of freedom. So in order to reduce these redundant degrees of freedoms, I can replace, for example, this SP and S mu nu in terms of V mu and A mu, or you can do it inversely if you wish. Then this 10 equation just reduced to 6 master equations, which allows me to perturbatively solve for the Wigner functions. Moreover, I want to mention that some of these replacements has the non-trivial physical meaning. For example, when you replace P, the pseudoscalar, by this A mu, then this equation basically implies the anomaly equation with the mass corrections. So when you perturbatively solve these Cardinal band equations, you actually implicitly include some of these quantum effects. Okay, and so in the massless limits, it turns out that this SP and S mu mu's becomes decoupled from V mu and A mu. So the Wigner functions get simplified. So you only have these two components. And you can also then recombine these V mu and A mu in terms of just the Wigner functions constructed by, for example, left-handed fermions, or the one constructed by just right-handed fermions. Again, this is also because of this spin enslavement. So you only have 2 dynamical degrees of freedom in the massless case. And then they can be characterized by these distribution functions of the right-hand and left-handed particles for the leading order Wigner functions for the right-hand and left-handed fermions is here, right? And here, this epsilon bars is represented as sine function. So I have this is to include both the particles and antiparticles contributions. Okay, so this is just the leading order. So now we want to move to the next leading order at order of H bar to include the quantum corrections for Wigner function. Okay, now firstly, you will find there exists this kind of quantum corrections is led by the electromagnetic fields to modify your on-shell conditions. From, for example, the magnetic moment coupling. But more importantly, I will focus on this term, that is the so-called side jump term, which lead to these magnetization currents, and it lead to the partial contributions of a chiral vortical effect or the anomalous Hall effects. Notice that this turn actually is induced by some kind of phase space inhomogeneities of the distribution functions in the free streaming case. So in this d mu, so here this contains the delta acting on F, which contains the space-time derivative and also the momentum derivative when you the background electromagnetic fields. Moreover, these terms can also include the collisionless corrections, but this is actually a kind of non-equilibrium corrections. And this term is coupled to the so-called spin tensor, which actually depends on the frame vector. So basically, this frame vector exists technically just because you have the freedoms to make the decompositions of your Wigner function. So I forgot to remind you, this is just for the right-hand Wigner function. So I exclude this sub-indices right here. Okay, so now, because this S mu nu depends on the frame vector, it also suggests that this distribution function is also frame dependent. But you should always remember that the full Wigner functions will be always frame independent. Okay. So now with these Wigner functions and also the Carnot band equations, one can then derive the quantum kinetic theory or the chirokinetic theory. And for conveniences, I will just work in this constant frame vectors. So you can even make these frame vectors local if you wish. But then if you take the constant frame vectors, this is the chirokinetic theory. So you firstly see this kind of change of dispersion relation explicitly from the magnetic moment coupling. And also this part is just the standard velocity equation, but then you also have these quantum corrections led by the coupling between the electromagnetic fields and the spin tensor. But more importantly, I would like to focus on just the collision terms. So for collision terms, this Q dot C is the classical one, so which can be written in this form in terms of self-energies. And you also have the quantum corrections from the electric field. But more importantly, I would like to focus on these terms. So for these terms, you can explicitly see now there exists the gradient terms acting on the self-energy and couples to the S alpha beta. So this term is actually a kind of source which can generate some vorticity corrections in your collision term, because for example, if you assume now the median is in thermal equilibrium, but it has rotation, so then the gradients is acting on these fluid velocities coupled with S alpha betas can lead to the vorticity terms, right? So this is actually the important contributions which can generate the vorticity corrections from the collisions terms. But this is not only in H bar corrections. In fact, even for the sigma lesser and the sigma greater, there could be also implicit H bar corrections coming from the Wigner functions are included. So you have to combine both effects. So when I turn off the electromagnetic fields, remember then the only quantum corrections will appear from the collisions terms. Okay. So now the strategy is very simple. So you have the CKT, then you just solve for the distribution function, you put it back into these Wigner functions, then you could calculate this basically the spin currents density in the phase spaces from the contribution of the both right-hand and left-hand fermions, right? So let me provide you the kind of concrete examples to see how these vorticity corrections can appear in collisions terms. So unfortunately, the example I'm going to show you is not in heavy ion collisions. It's in the context of this neutrino absorption and emission process in the core collapse supernovae. But because this is a kind of weak interaction and neutrino is always left-handed, so actually it's a very ideal circumstances to have the maximum chiralities, which is suitable for chirokinetic theory, right? So now I have the neutrino, which scatters with the neutron and becomes the electrons and the protons. Okay. So here I just write down this kind of collision terms. From this, you can explicitly read out what self-energy is for this scattering process as an exact example. So I consider the weak, this Fermi effective theory. So this GF is the Fermi constant, right? And GV and GA represent the vector and the actual coupling, okay? So in this context, we can basically assume the neutron and the protons and also the electrons in supernovae are in thermal equilibrium, okay? But only the neutrino is always out of equilibrium. So we want to write down this kind of chirokinetic theory for neutrino, then this gamma lesser and the gamma greater just represented the emission and absorption rates of neutrinos, right? And I also work in this constant frame vector here, okay? Now, with the certain, sorry, I want to mention that in here, I will treat the neutrino and the electrons as massless particles. So they can have the quantum corrections from the Wigner functions I just showed you, right? So this corresponds to the Wigner function of a neutrino, Wigner function for electrons. But for nucleons, they are actually very heavy. So the quantum effects will be suppressed. So here I just inputted the classical Wigner functions for nucleons represented by W and W prime, okay? Right. So with this, and then this emission and absorption rate, after doing some approximations, you can see now this is the classical contributions for the sigmas at the classical levels is coming from this one. But then there exists the quantum corrections is coming that by vorticity and magnetic fields, which come from the equilibrium Wigner functions of electrons here. So at the order of h bars, these electrons can have this vorticity and the magnetic field corrections when it's in equilibrium. Moreover, you also have these derivative terms acting on the self-energy, which give you the extra contributions from the vorticity. So in the end, you have these analytic expressions here. So for the this emission and absorption rate, this classical part just depends on some coupling constant and the nucleon density. And also now you have the explicit quantum correction laid by Q dot omega and the Q dot P with the non-coefficient here and here. So that is a kind of a very concrete example to show how this vorticity or even magnetic fields enter this collision term as a kind of quantum corrections in scattering process. In heavy ions collisions, you have heard the talks given by Sun. So they introduced these kind of chirotransport models with collisions incorporating sidedromes inspired by the chirokinetic theories. And it seems that they can possibly resolve these side problems for longitudinal polarizations. So I will say perhaps a more detailed comparisons between these chirotransport models and the chirokinetic theory from Wigner function approaches might be helpful for us to have better understanding of this underlying physics. Okay. So now, if we are only interested in the massless fermions, then this is the end of story. We just use chirokinetic theory. So if we are only interested in the U quark or D quarks in the QGP, then this is probably fine. But if we want to consider the stranger quarks, then we cannot neglect the mass. It turns out that there exist very sharp differences between the massive case and the massless case. Because for the massive fermions, the spin is no longer enslaved by chirality. Okay, so it has to be treated as a new dynamical degrees of freedom. And one can also understand this is by just construct the Wigner function directly from the quantum field theory. So here I just write down these Wigner functions from the expectation values of two Dirac fields, and I neglect the antiparticle contributions. So it's U and U bar basically correspond to the wave functions of the psi and psi bar, right? And you also have this expectation value of the density operators for the creation and the annihilation operators from these two fermionic fields. Notice now that for the massive fermions, we have the chirality mixing. So this helicity indices here for S prime and S, which represent the helicity of these two fermionic fields, can be different. That's not the case for the massless case. Then in massless case, S always equals to S prime. Then we just have 2 dynamical degrees of freedom. But now we have 4, right? So actually, you can also use these computations by further performing these P minus expansions to calculate the Wigner functions directly. This actually gives you also the H-bar corrections for the free fermions. But one can also use this. One can also solve these Wigner functions from perturbatively from the Cardano band equations. Okay, so now we for simplicity we first consider the free streaming case. So we decompose these Wigner functions into this up to order of H bar, right? So for the leading order, the classical part now both these V mu and A mu components now do not only depend on the vector and the actual charge distribution function. We need to introduce another dynamical variables here. So for massive fermions, you are no longer able to work in the wild basis. You have to work in this vector and the actual basis. So here I actually introduce this A mu, which is I call it the spin 4 vectors. So in total, this FV, FA, and A mu should contain 4 dynamical degrees of freedom, and this A mu should satisfy some constraints. Particularly when you take the massless limit, this A mu should reduce to the momentums to capture these spinning statements for the massless particle. In fact, sometimes it's not necessary to really decouple this A mu and FA. The reason I write it into 2 terms is just because it's easier to make the comparisons with the massless limit, right? Okay, so with that, you can get the leading order kinetic theory. For the vector part, that is nothing but the Villosov equation. For the actual vector part, you actually get the so-called relativistic versions of these BMT equations derived in the condensed matter physics communities long time ago. But this is kind of relativistic versions. And then if you take n equals to 0, then this equation can directly reduce to the Villosov equation as you expect, right? Notice that at the classical level, there exists no mixing between the vector and the actual components, but these mixings will appear at the quantum level at the order of H bar. Okay. So at the order of H bar, again, then I can perturbatively solve for V mu and A mu now. They actually take a similar form as the massless case, right? So you can see they also get these modifications on the dispersion relations from the background electromagnetic fields. And they also have these so-called magnetization current terms, which is led by the spin-orbit interaction. So here I will just abuse these terminologies. When I mention the spin-orbit interactions, I actually refers to the kind of entanglement dynamics between the vector and the actual charge, okay, in that sense. Okay, so this kind of magnetization current term also contains now the derivative acting on the distribution function. So they can also give you some kind of vorticities corrections, right? And they also depends on this frame vector. And if you take the massless limits, then this 2 function just reduces to the side-joint terms in CKT, which will contribute to the chirovortical effect. I want to make a comment here. So basically, you are free to choose your frame vector. Particularly for the massive fermions, you can actually work in the rest frame. That is, you can choose m mu equals to q mu over m. And if you do that, these terms will then vanishes, and then you will have mass terms at the denominators of this term. But then, so the Wigner functions could be simplified, and also the quantum kinetic series will be also simplified. But the price is that then you may not have the direct smooth connections to the massless limits. So when I do this, basically these expressions will reduce to this form found in some of previous papers. Okay. But with this, then I can also derive this quantum kinetic theory. And for the free streaming quantum kinetic theories, now I call it the actual kinetic theory because it contains not only one scalar equations, but also another actual vectors kinetic equations. So the leading order, this is Vilasov, and this is the BMT. And now you have the H-bar corrections is coming from this kind of terms. So this delta and the nabla actually incorporate the momentum derivative associated with the background electromagnetic fields. So this only comes from the electromagnetic fields correction. So I am not particularly interested in this kind of complicated corrections, and maybe it's not so relevant to the context of heavy ion collisions, because if we assume the magnetic field is too weak. Okay, so it turns out this is a similar story that the kind of vorticity corrections is, which may affect the spin polarization should come from collisions, also for massive fermions. Now, the question is then how to include the collisions. Okay, so for Dirac fermions, then it's to solve this Cartan-O'Bank equation, it's more convenient to also decompose this self-energies based on the Clifford algebra. The point is that basically this scalar term and the vector terms always appears in your classical Boltzmann equation. So by comparing this with some classical cross-section, then you will figure out how to write down your Wigner functions in terms, how to write down your self-energies in terms of the Wigner functions, right? So this can help you to also pin down the contributions is coming from other components, okay? But if you just naively insert this into the Cartan-O'Bank equation, then the Cartan-O'Bank equations becomes too complicated to solve. To overcome these difficulties, we actually propose a kind of power counting schemes, which is actually practical for the studies of polarizations, spin polarizations in heavy ion collisions, assuming this is also triggered by some vorticity, so gradient terms. So we assume the vector component, which is at the order of h bar to 0, but for A mu, we assume it's at the order of h bar, because basically the spin is kind of quantum object. And also, if this A mu is induced by some gradient term, then this is also at order of h bar. So it's a kind of natural power countings for our systems we are interested, right? With that, we can also have these following power countings for the self-energies, except for this sigma p, that we cannot really determine, but we will neglect these terms because it mostly just come from some condensate contribution. So it's not very likely this can lead to the contributions for the system we consider. Okay, so with these power countings, we can accordingly construct the so-called effective actual kinetic theory with collisions. Of course, again, this is not only in the approaches. For example, you can also try to incorporate some kind of quantum corrections from the collision terms based on this Boltzmann equation with the non-local collisions. I think Noras will talk more about this, and also there are also a different approaches from Joe. And so just see the follow-up talks today. Okay. Now, let me mention that with this power counting, so then we can get the leading order Wigner functions for V mu and A mu, right? So we can now only focus on just the leading order contribution. For V mu, the leading order contribution is just the classical contribution. So this is a classical expression of V mu. A mu, the leading order contribution now start at order of h bar because we take Fa at order of h bar, right? So the full expression is at order of h bar. Again, this now include this kind of space-time derivative acting on the distribution function, and he also incorporated the collisional corrections, but now only the vector components of self-energies is included from this power counting. For the kinetic equations, for the SKE, we just get a standard Boltzmann equation as leading order kinetic equations, which is include the classical collision term. We are more interested in the actual kinetic equation now. The leading order equation is already at order of h bar. So here I just use this h bar to specify some explicit gradients corrections. So I will call it the quantum correction. So basically, the collision terms now contains two parts. One is from the classical part, which lead to the spin diffusion. But you need these quantum corrections to get the spin polarized from the couplings to the vector charges. Okay. So the full quantum kinetic theory or full AKE will be very complicated. It contains also the contributions from also the background fields, but so it's probably not necessary to show that full expression. So I will show you just the simplified case by setting the again the constant frame vector and then term of just these background fields. So the only quantum corrections again can come from just the collision part. So now you have the AKE like this form. Okay. This term correspond to this classical part, which gives you the spin diffusion in general. And then these terms give you these spin polarizations, actually the partial contributions of these spin polarizations, but you can see this these kind of corrections is again are led by this kind of gradients acting on the self-energies. But again, like the chirokinetic theory case, this sigma A mu and also sigma T, they can also contain the quantum corrections is coming from the Wigner function. So you input depending on your systems. Okay, so you have to again incorporate the both h bar corrections to get the full spin polarization terms in your collisions. Okay. Now let me provide you some examples for the applications. Actually, in our papers, we also use this AKT to study the spin diffusion parts for the massive quarks in the weakly couples quark-gluon plasma. So we only calculate this classical contribution, but we plan to calculate the quantum corrections in the future. It's more involved. So basically, the purpose is actually to reproduce this result also found by Hong Yi and his students from somewhat different approaches, but basically we have the same setup. So we consider the sufficiently heavy quarks, which allow us to neglect the Compton scattering, and we also apply the HTL approximations, which give us the leading logarithmic results. So I want to mention some details of the calculation of the self-energies in this interaction process. So basically, we consider these quarks, which scatters with QGP. This is a cut diagram, okay? Now, this S of Q minus P is basically this outgoing outgoing quarks here. And this GF and GF dagger correspond to these two intermediate photons. They are Feynman propagators. And this pi alpha beta is nothing but these 2-point functions of a QGP. If you just consider the classical contributions, then this pi alpha beta is always real and symmetric in alpha and beta. But if you include the h-bar corrections, this can be imaginaries and also anti-symmetric. But even with that, this sigma is still real. But this can also lead to the kind of quantum corrections, for example, for this sigma A and the sigma T I just mentioned on the previous slides. Okay. But the point is that with just classical contributions, then the outcome is that in equilibrium for massive fermions, this vector charge distribution function just reduced to the Fermi-Dirac forms, and the spin path just dissipate. So it becomes zero in equilibrium. So you need quantum corrections to give you the polarizations. So actually, I just found these recent papers by the Fu and Shu-Lin. They actually consider the quantum corrections is from the massless fermions in this kind of quark loop. So when you include the Wigner function with H-bar corrections here, they can explicitly show now this will lead to the anti-symmetries and the imaginary quantum corrections is associated with the vorticities from QGP. Actually, what they consider is QED, but this is a kind of similar story. Yeah. Moreover, in another papers done by Qinghua's group, and also as you heard from Ziju's talk several days ago, they use these AKT formalisms to deal with the NJLO models, and they found that with these detailed balances by requiring the vanishing collision terms, now they can get the spin polarizations of these actual vector components. So they include both the diffusion part and the quantum correction part, so they can get this form, which is led by the sum of vorticities in local equilibriums, and then this expression actually also matches what have been found in some like statistical approaches in global equilibrium. This work actually also reminds me that actually we could also have the local equilibrium for massless fermions through just 2-to-2 scatterings in chirokinetic series. Okay. Now let me switch the gears to discuss about the spin-1 massless bosons. So in fact, if we want to really study the spintronics in QGP, certainly we cannot neglect the polarized gluons, right? And although it's not clear as to how to directly measure the spin polarization of gluons, but at least this gluon can indirectly interact with the fermions and modify which may possibly modify their polarization, right? So basically, the spin polarization of fermions could be indirectly affected via, for example, the competence scatterings, even in QED, right? So it's quite natural to pose the questions: is how about the Wigner function and the quantum kinetic theory for polarized massless spin-1 bosons such as photons up to order of H-bar. So you have already heard the previous talks by Andre, but I will mention some of results found by my recent work, which may appear on arXiv soon, which is in collaboration with Koichi, Yoshimasa, and Naoki. Okay, so we basically use a kind of different approaches to derive this kind of Wigner functions and the kinetic theories for photons. So we want to make more direct connections between the right-handed and left-handed photons and the right-handed and left-handed fermions in the massless case, because they are both massless particles, right? So we actually adopted the constructions of these Wigner functions from just field series calculations. For yeah, here is the free photons, right-handed photons. Okay. Now the question is just how to.
Di-Lun, you have only 2 minutes.
Okay, I will speed up and try to finish this. Okay, so basically now the point is that to write down these polarization vectors of right-handed fermions in a more general way, to which explicitly depends on momentum. And it turns out that you can use these spinner technologies to represent these polarization vectors in terms of actually the wave functions of the massless fermions. for example, for the right-hand photons, you can write in terms of the wave function of right-handed fermions. So because basically they have the same degrees of freedom in such a case for massless photons, right? So I take a Coulomb gauge. This L mu basically represents the temporal directions to define Coulomb gauge. So the point is that you can write down this polarization vector in terms of the positive and negative energy eigenmodes of the right-handed fermions. Then you can calculate this to get calculate the Wigner functions to get these H bar expressions. This is Wigner functions for right-handed photons. You have the classical part, which is symmetric. This P mu nu is just the usual polarization usual tensor structures of the Wigner functions of photons. But then you also have the quantum correction, and also this is anti-symmetry part, which is imaginary. And this is related to the spin tensors of photons, which is 2 tensors of the spin tensors of fermions, right? Combining the right-handed, left-handed contributions, then you could have this Wigner function for photons is governed by, again, you can define the so-called vector and actual charges for the polarized photons. And you can use this to calculate, to study, for example, the spin or helicity currents of photons. As we know, the Chern-Simons current is gauge dependent, so we may alternatively study like the Zilch tensor, which defines the optical chirality, and then this is also gauge invariance. So in fact, we use these Wigner functions, and then we study the thermal equilibrium conditions by requiring the explicit gauge independence of Zilch. Then we get the distribution functions with the spin vorticity couplings, and also reproduces the results for the Zilch currents as found in Xu Guang's paper. Moreover, we can now also derive the Kadanoff band equations for photons, for polarized photons with the quantum corrections in the collision terms. So this is the standard approach, but we have the extra contributions if you want to include the anti-symmetries contributions of this G mu nu. So these extra contributions in the collision part will contain, again, some kind of gradient term acting on the self-energies. This part is important to satisfy the gauge constraint up to order of H bar. So usually people only consider the gauge constraint at leading order. With that, you can also derive the quantum kinetic theory for photons, and we actually apply some kind of similar power content schemes as the fermions, and also further assume some properties of these self-energies for photons. Then we can get the effective quantum kinetic theory, which describe the vector charge evolution and the actual charge evolution of photons. So this is like the AKE of photons in a sense, which also contains the quantum corrections from collisions coming from some kind of derivative acting on the self-energy. So assuming that there exists some rotation of the systems when photons scatter with the fermions, then this may also possibly lead to the polarizations. Okay, then let me make the quick conclusion and outlook. So I have shown you that we have obtained these generic forms of effective quantum kinetic theory for spin 1 half fermions, and also the massless spin 1 bosons from the Wigner function approach. And quantum corrections in collisions will be essential for the spin polarizations, is that by vorticity or other non-equilibrium effects coming from gradients terms. But details matters. So in order to have the application to weakly coupled QGP, we need further calculation for the detailed scheduling process therein, okay? And of course, the final goal is to simulate the full quantum kinetic equation out of equilibrium, but it's always easier to study the near equilibrium corrections and get more physics from there. And also you can use that to construct, for example, spin hydrodynamics. And now in the end, it's interesting to ask the question, what will be the spin polarizations of fermions and bosons when they coexist in this kind of quantum kinetic series pictures? Thank you.
Okay, so it's time for discussion. Any comments and questions? Ah, yes, I see. Hong, please.
Yes, thanks, Di-Lun, for a very nice talk. I have a question on page 16. Could you go back to page 16? You mentioned about, yeah. So you mentioned about this antisymmetric part of gluon self-energy that
Yes.
could exist in general. I think I have a just a short comment that in the present, first we can show that this antisymmetric part, if you assume rotational symmetry respect to this momentum P, it can be shown that it is CP and is parity-ode and also CP-ode, and which means that it can exist only in the presence of axial charge.
Mm-hmm.
And we actually introduced this concept before as parity-ode spectral density. So I just want to mention that that part contains information about the axial charge of the system, which
Yes.
could be related to spin, but not always, right? The axial charge is just a helicity charge, not the spin polarization itself. So yeah, so that was just my comment.
Okay.
And
Mm-hmm.
yeah, and I actually have a question about your spin one boson system. I just
Mm-hmm.
wonder whether in very low energy limit, the spin vorticity coupling might flip this effective energy entering the Bose-Einstein distribution. I think this was also discussed before, but in that case, would we expect actually instability
I
in
think the problem is
energy?
that with this H bar expansion, then usually, basically, you cannot really assess the zero energy limit, right? Basically, because it depends on H bar expansion. So this Q mu has a infrared cutoff, which is governed by the gradient scales in your system. So I don't think we can possibly see that kind of purely quantum effect. I think this is
But
perhaps.
yes, but if you want to compute, say the total spin polarization of a system, then shouldn't we actually worry about this some large contributions from low energy limit? Because if they diverge, if distribution diverges, then the total spin polarization might get diverging contribution from those low energy region. Does it make sense? Yeah.
It's I guess I will say in principle that could be possible, but this is like the similar questions like for example, when we consider this application of this AKT for fermions, so in this case we also make some cutoff based on this thermal masses, right? So in the medians, I think we could probably at least add some kind of cutoff there. But as you say, if really you find that the infrared contributions becomes very important, then I will say then that kind of physical phenomenon is perhaps can not able to be captured by this quantum kinetic theory. So it depends on what kind of physical observables you want to consider, and if indeed this kind of infrared contributions becomes very important, then within the current framework, then probably we are not able to deal with that. I will say
Yeah,
that's.
I have to cut the discussion here, but maybe
Thank
we can move part of the discussion to the round. Oh, sorry. So there's no round table discussions.
There's no round table today.
Later today, right? Okay, so let's move to the next question. Shu, please.
Okay. Di-Lun, thanks for the nice talk. I have a question on your H-bar expansion for the collision term in your page 10.
Page 10, okay.
Yes.
Yes.
So, you have this two small boxes.
Right.
This is H-bar correction, non-gradient H-bar correction, right?
Actually, they are gradients correction, but it's encoded in some Wigner functions in the scheduling process. For example, actually, in this case of this neutrino absorption emission process, that kind of corrections comes from, for example, I mentioned that this is like a sigma omega, which contains the vorticity corrections that by actually this Wigner function of electrons in equilibrium. Okay, so it's still a kind of it's still a gradient corrections within this framework. So also it can contain, for example, magnetic fields corrections. Yeah, but it's just not explicit, let's say, in this expression, because this is a general expression, so you actually don't know whether there exists H-bar correction for this sigma less or sigma greater or not. You have to deal with the real scheduling process to figure out whether they exist or not. Yeah, but they are still gradients correction. Yeah.
Okay, so maybe I have a very short question. So suppose you have weak electromagnetic field and a weak gradient, space-time gradient. Can I say that there's no H-bar correction for the second kind?
You mean if the electromagnetic fields are very small?
The only gradient is from the external field and the external space-time homogeneity. Can I say the second kind H-bar correction
yes.
is not existing?
Yes, so if you assume that the system, the electromagnetic fields are really small, then the only corrections is coming from the space-time gradient terms, right? But notice that even in that case, the Wigner function they're in, for example, for these electrons, you can also have the gradient corrections is coming from the vorticity, for example, or even the gradient of temperature, etc. We actually do not consider that here, but it could be possible. Yeah.
Okay. Thanks.
Yeah. The next question, Shi, please.
Hello. Thanks for the nice talk. So actually, I also have a question on the page 16 about the spin diffusion.
Okay.
So I understand if the particle interaction with QGP at the equilibrium, the spin should be 0. The total polarization something should be 0. My question is, what happened if the particle does not interact with the QGP but only interact with themselves? So in that case, in the equilibrium, what happened for the A mu Fa for this term? Is this term still be 0 or something else?
Sorry, what did you mean interacted with itself but not QGP? So are you concede? Let me understand your question.
Maybe let me put my question in a clear way. So you derive the chirokinetic equation for the massive particles. Can you prove or can you see the total angular momentum conservation during the collisions?
That is actually a good question. So I think this is a bit tricky because actually I don't even have a clear answer because it's Actually, in the free streaming case, in the free streaming case, as you know, there exists this angular momentum conservations characterized by the Khatanov-Bent equation, right? Like this, one of the Khatanov-Bent equations in the free streaming case just reveals the angular momentum conservations. But if you have a collision, then there will be also extra terms. So in such a case, I don't really know. But the problem is that actually, I think what you consider is the angular momentum conservations is after you integrate over the momentum, right? So that is basically the usual angular momentum conservations we are talking about. But let's say we are actually interested in a spectrum, right? So in such a case, I don't really know whether these evolutions of all these distribution functions in the phase space can directly reflect this kind of angular momentum conservation. Although I think in general they should be conserved, but I'm not sure. Okay, I will say I still don't have a very clear picture. For example, for this actual kinetic theory, how this is related to the angular momentum conservation, because if you integrate over the momentums, right, this is not really the angular momentum conservation equation. So
Okay.
So yeah, I cannot answer you.
Maybe we can discuss later.
Right.
Thank you for your answer.
Yes, I stopped recording.